This is a 2024 mock chemical equilibrium question. So the first thing we're asked to do is our definition to explain chemical equilibrium. So chemical equilibrium is the state of dynamic balance in a reversible reaction where the rate of the forward reaction equals the rate of the reverse reaction. B. Sulfur dioxide SO2 and nitrogen dioxide NO2 react in the following equilibrium reactions. So we have our reaction here. Okay, so sulfur dioxide SO2 and nitrogen dioxide, okay, are in equilibrium with SO3 sulfur trioxide and NO nitrogen monoxide. Alrighty, so a chemist heated 8.32 grams of sulfur dioxide, so that's this one, the reactant, and 4.6 grams of nitrogen dioxide, NO2 reactant, together in a closed 1.0 litre container at temperature T. Okay, so what we're told here is we're given our masses of our reactants, and we're also told that the volume of the container is 1 litre. You're asked to write an expression for the equilibrium constant for this reaction. So that would be, if I write out, remember when you write out an equilibrium constant, you must always write out the equation it matches up to. So remember for Kc value, okay, we're looking at the concentrations of products on the top row and concentrations of reactants on the bottom. We're using square brackets to show concentration values, and we are raising the brackets to the powers of the numbers of moles in the balanced equation. Now in this particular question it's all 1, 1, 1 and 1, so therefore the powers here are all invisible ones also. Okay, another thing to note is these concentrations are being multiplied by each other. You're not adding them, there's no plus signs in between them or anything like that. They're just right beside each other, they're multiplied by each other, top and bottom. So just to go over that once more, the Kc value for this question is the concentration of the products, SO3, times the product NO, divided by the concentration of SO2 times the concentration of NO2. Okay, in the next part, in part 2, we're asked to calculate the value of Kc under the conditions described above based on the chemist's report of a 4.8 gram yield, so 4.8 gram yield of sulfur trioxide at equilibrium. So we're told that at equilibrium we have made 4.8 grams of SO3. So we're going to set up a table. We have our reactants SO2 and NO2 and our products SO3 and NO. Okay. Now we're not told how many moles we have of them to begin with, but we are told how many grams. So let's work out how many moles we have over in rough work. So remember in rough work here we have our good night Mr. Tom triangle, so that'll allow us to work out the number of moles is equal to the grams divided by the relative molecular mass. So we were told in the question that we had 8.32 grams of sulfur dioxide. So let's just work out the relative molecular mass of SO2. So we have sulfur, which has a relative atomic mass of 32, and 2 oxygens, so that's 2 times 16. So I get 64 as the relative molecular mass there of SO2. So to work out my number of moles, I take the grams, 8.32, divided by 64, and I have 0.13 moles. Similarly, I've worked out a similar calculation for NO2. So 4.6 grams of NO2 divided by its relative molecular mass of 46 is going to give me 0.1 moles of NO2 at the start, okay? And then at equilibrium we're told we had a yield of 4.8 grams of SO3. Working out the relative molecular mass of SO3, it's 80. And if I divide 4.8 by 80, so to get the number of moles, it's grams divided by relative molecular mass, and I get 0.06 moles. Alright, so I can use these values now in my table. So remember with your table, we think of ICE, initial, change, and equilibrium. So the initial amounts I have of SO2 are 0.13 moles, I just worked it out over in rough work, 0.1 moles of NO2 from rough work, and at the start I had no products, I had no SO3 and no NO. Okay, now I'm told that I made 0.06 moles. Well, I worked that out. I was told that I made 4.8 grams of SO3. Okay, and I worked that out to be 0.06 moles. So that means I'm adding in 0.06 moles of SO3, okay? Because my reaction ratio here are all 1:1, that means if I'm making 0.06 moles of SO3, I'm making the same amount of NO, okay? So I'm adding 0.06 moles of NO. It also means that I'm losing 0.06 moles of SO2 and 0.06 moles of NO2 throughout the reaction. So at equilibrium, I end up then with 0.13 moles is what I started with of SO2 minus the 0.06, and that gives me 0.07. So 0.13 moles minus the 0.06 gives me, at equilibrium, 0.07 moles of SO2. For NO2, I started with 0.1, I'm losing 0.06, therefore at equilibrium I have 0.04 moles of NO2. I started with no moles of SO3, I'm adding 0.6 moles of SO3, so that gives me 0.06 moles of SO3 at equilibrium. And for NO, it's a similar story, nothing to start with, adding 0.06 moles of NO. Alrighty, so they're the number of moles at equilibrium. So now we just have to convert that into a concentration. So we're remembering our not very complicated triangle, complicated triangle. So to work out concentration, it's number of moles divided by volume. Okay, now the volume here is a nice easy one, it's just 1. So when you divide the number of moles by 1, obviously you end up just with the same number of moles, okay? But just do write it out all the same to show that you understand this step. Okay, so remember the aim of the game here is to work out the Kc value. So we have our expression up here. Okay, so simply what we do is we just substitute in the different concentration values at equilibrium. Okay, and we have those from our table. So the Kc value is the concentration of SO3, okay, at equilibrium, times the concentration of NO at equilibrium, so my products, divided by my reactants, 0.07, 0.04, okay. I check my equilibrium constant expression, make sure I have no powers that I need to, allow for. All the powers here are 1, so when I work that out on my calculator, I simply get 1.286. So that's the Kc value for this reaction. In part 3 of section B, we're told Henri Le Chatelier studied equilibrium in industry in the late 19th century. According to Le Chatelier's principle, how was the yield of nitrogen oxide affected by increasing the pressure at temperature T? Explain your answer. Okay, so let's just look again at our equilibrium reaction. Okay, so we have SO2 and NO2 in equilibrium with SO3 and NO. Okay, now they're all gases, okay, which is something worth noting. And very important to note here is we have the same number of moles of gases on both sides. So I have 2 moles here, 1 plus 1, okay, on the reactant side. And I also happen to have 2 moles of product on the product side, okay? So the number of moles in this particular question are the same. So that's going to have an impact on our answer here, okay? So in the question we're asked to explain how the yield of nitrogen oxide is affected by increasing the pressure at temperature T. Now normally if we were to increase the pressure, and if we have an all gaseous reaction like we do here, normally what would happen would be that an increase in pressure would favour the reaction that will reduce the number of molecules, okay? But in this particular question, because we have the same number of molecules on either side, shifting to the left, shifting to the right is not going to alleviate the pressure, okay? So there's no effect on the yield of nitrogen oxide with an increase in pressure. And the reason being, as we've just said, because we have an equal number of gas molecules on each side. So there is no advantage to shifting to the left or the right here. It's not going to have any effect on the pressure. Okay. In part C of this question, we're told a student was provided with the appropriate glassware and laboratory apparatus and the following chemicals: iron 3 chloride, FeCl3, potassium thiocyanate, KCNS, and hydrochloric acid, HCl. You're asked to describe how the student could use the chemicals listed above to establish a chemical equilibrium. Okay, so what you could say there is that you could mix your iron 3 chloride and your potassium thiocyanate in a boiling tube, and then you could add hydrochloric acid. Okay. Part 2, write a balanced equation for the equilibrium reaction. So let's look at this equilibrium reaction. So the iron chloride, FeCl3, is going to react with the thiocyanate anion, okay, from the potassium thiocyanate, okay. So FeCl3 and CNS minus will establish equilibrium, okay, and they're going to produce iron thiocyanate, okay, so FeCNS2 plus and 3 chloride anions, okay. Now, the iron chloride is a yellow colour when it's in solution, and the iron thiocyanate is going to be a red colour, okay. Part 3, we're asked, describe how the student could then demonstrate the effect of concentration on the chemical equilibrium. State the observations made during the demonstration. Okay, so let's take a look at the effect of concentration in this equilibrium. So if you look at the balanced equation here, if we are favouring the forward reaction, that's going to result in a lot of the red product being made, the iron thiocyanate being made, okay? If we're actually favouring the reverse reaction, the back reaction, if we're shifting to the left, we're going to favour the production of iron chloride, which is a yellow colour. Okay, so let's look at the effect of adding in more HCl. If I add in more HCl, I'm increasing the amount of Cl minus ions, okay? So that's a stress to the system. So according to Le Chatelier's principle, if you have the system at equilibrium, and if we apply stress, so add in extra chloride anions, it's going to want to adjust to relieve that stress, to oppose that stress. So it's going to want to use up the chloride ions. So therefore, the back reaction is going to be favoured, okay? And we will see that we're going to be making more iron chloride, and the solution is going to turn more yellow, okay? So that indicates shifting to the left, okay, favouring the reverse reaction. Another way of looking at this is if I was to add more iron chloride or more of my potassium thiocyanate, so I'm increasing the reactants, that's going to basically shift the reaction to the right. It's going to favour the forward reaction to use up these reactants. And therefore, I'm going to be making more products, and the solution is going to turn more red, okay? So if it shifts to the right, favouring the forward reaction, the reaction mixture will turn more red.